What if the first warnings of a monster storm weren't in the clouds, the tides, or even the wind, but in the invisible waves carrying our voices and guiding our satellites? What if the breakdown of a radio signal, the sudden drop in GPS accuracy, or an eerie crackle of static over the airwaves were not just glitches, but nature's own announcement that a cyclone was gathering strength? And what if, long before the eye of the storm was visible, the atmosphere itself had already begun to scream through electrical and magnetic anomalies? For decades, meteorologists have relied on physical signs, cloud formations, tidal surges, shifts in humidity, to track storms. But in recent years, another frontier of research has emerged: the electromagnetic environment of the Earth. As hurricanes form and intensify, they disturb not only the ocean and the lower atmosphere, but also the ionosphere, the magnetic fields, and the radio spectrum we use for communication. NASA's Geospace Research Division has documented ionospheric disturbances during cyclonic formation, while studies at the Jet Propulsion Laboratory, JPL, have revealed patterns of electromagnetic anomalies and unusual lightning behavior that precede Category 4 and 5 hurricanes. To most people, these changes are invisible. Yet for those who depend on radio, GPS, or even simple AM transmissions, the signs are clear. The storm is already interfering with the world above. One of the most common experiences reported before major hurricanes is the sudden loss or degradation of radio signals. Long-range AM broadcasts, which normally travel hundreds of kilometers at night by bouncing off the ionosphere, become distorted, fading in and out unpredictably. Fishermen in the Caribbean have long noted how their radios die hours before a hurricane arrives, leaving them without communication even while skies above still appear calm. In the modern age, pilots, ships, and even ham radio operators report similar anomalies: static-filled transmissions, sudden loss of clarity, or complete blackout of certain frequencies. These are not coincidences. Research shows that cyclones disrupt the ionosphere by altering electrical currents and introducing large-scale convective disturbances. The result is a noisy, unstable medium for radio propagation. GPS systems, too, show measurable degradation before storms. Normally, satellites transmit signals that travel through the ionosphere, where they are slightly delayed, depending on the amount of charged particles in the path. But as NASA's Geospace researchers have shown, cyclones inject turbulence into these upper layers, creating small-scale irregularities called scintillations. For a GPS receiver on the ground, scintillation looks like flickering or loss of lock, reducing accuracy from meters to tens of meters or more. In aviation and shipping, this can be dangerous. Pilots approaching airports in storm-prone regions have reported sudden GPS errors, while maritime operators describe moments where navigation systems lose reliability hours before winds pick up. The storm announces itself not just in the ocean's waves, but in the radio waves linking Earth to space. JPL studies have added another dimension: unusual lightning patterns surrounding intensifying storms. Instead of random strikes, researchers have observed what they call lightning rings, concentric circles of electrical discharge around the developing cyclone. These rings are thought to form as convection organizes in spirals, concentrating charge separation into coherent structures. While invisible to the naked eye from space, ground observers sometimes notice unusual electrical behavior: flickering power lines, bursts of static in radios, or even aurora-like glows in the upper atmosphere. For scientists, these anomalies are valuable indicators that the storm is about to intensify. For ordinary people, they manifest as strange malfunctions in the technologies they use every day. Historical cases illustrate these phenomena vividly. Before Hurricane Katrina in 2005, ham radio operators across the Gulf Coast reported unusual static levels and difficulty maintaining connections, even though the storm was still offshore. During Typhoon Haiyan in 2013, communication outages plagued rural Philippines hours before winds arrived, not only from infrastructure damage, but also from atmospheric interference. In Florida, before Hurricane Irma in 2017, GPS receivers in coastal areas recorded increased errors in vertical positioning, a subtle but measurable effect of ionospheric disturbance. Each example reinforces the same point. The storm's electromagnetic footprint arrives before its physical impact. But why does this happen? The physics is complex but fascinating. Hurricanes are immense engines of convection, moving heat and moisture from the ocean into the atmosphere. This vertical motion disturbs the ionosphere by sending gravity waves upward, oscillations that propagate far above the storm itself. These waves modulate the density of charged particles, creating regions of higher and lower electron concentration. Radio signals traveling through these disturbed regions scatter and refract unpredictably, causing fading, noise, and loss of lock. In effect, the storm shakes the sky itself, and our technologies feel the tremors. Electromagnetic anomalies also arise from the storm's own lightning. As convection intensifies, charge separation within clouds produces massive electrical discharges. Unlike ordinary thunderstorms, hurricanes generate lightning in organized bands, often aligned with their spiral structure. Each strike releases electromagnetic pulses across a broad frequency spectrum, from radio to very low frequency, VLF. Sensitive receivers pick up these bursts as pops, crackles, or even eerie continuous tones. Mariners before the satellite age knew to distrust their radios when storms approached because static levels would rise long before the first gale. Today, scientists use these lightning-generated signals as proxies for storm intensity, but the principle is the same. The cyclone speaks in electricity. Magnetic anomalies are less obvious, but equally real. JPL research has found that the immense electrical activity of hurricanes can induce small but measurable variations in Earth's magnetic field. Instruments called magnetometers detect fluctuations that correlate with the storm's growth. To humans, these shifts may manifest subtly. Some report compasses behaving strangely, while others describe unexplained interference in electronic devices. While still an emerging field, the evidence suggests that hurricanes, like earthquakes, produce electromagnetic signatures that precede their peak violence. The implications for survival and awareness are significant. While cloud formations and tides are visible to anyone, electromagnetic anomalies are harder to sense without instruments. Yet people who rely on technology often encounter them. A fisherman losing his radio, a pilot noticing GPS errors, or even an amateur radio operator struggling with static. All are experiencing the storm's electromagnetic shadow. Recognizing these signs can add an extra layer of preparedness, especially when combined with physical observations. Skeptics sometimes dismiss these phenomena as coincidence, pointing to other causes of radio disruption, such as solar activity. It is true that solar flares and geomagnetic storms also disturb the ionosphere. But careful research, including NASA's Geospace studies, distinguishes between solar-driven and storm-driven anomalies. The patterns are different, and the timing of disturbances around hurricanes is too consistent to ignore. In fact, some researchers now explore whether electromagnetic monitoring could enhance forecasting, providing another tool for predicting rapid intensification of tropical cyclones. There is also a psychological dimension. Survivors often recall how unsettling it felt to lose communication before a storm. In the Philippines, villagers described eerie silences on radios, as if the world had gone quiet before Haiyan struck. In the Caribbean, sailors feared dead radios more than dark skies, because silence meant isolation, just as the ocean grew dangerous. For modern societies, the loss of GPS and cell signals carries similar dread, highlighting how electromagnetic anomalies amplify the human sense of vulnerability before storms. Education about these clues is still limited. Most people are taught to look for clouds, winds, and tides, not for static on a radio or errors in GPS. Yet as science advances, integrating electromagnetic awareness into disaster preparedness may save lives. A fisherman who recognizes a sudden loss of long-range radio as a storm signal may head inland sooner. A pilot who understands why GPS errors spike may be better prepared for navigation challenges. Empowering people with this knowledge bridges the gap between cutting-edge research and everyday experience. Ultimately, the electromagnetic signals of storms remind us that hurricanes are not just local events, but planetary ones. They disturb not only seas and skies, but also the invisible layers of Earth's atmosphere that connect us to space. They shake the ionosphere, bend our radio waves, distort our navigation, and crackle through our technologies. These anomalies are not accidents. They are the storm's invisible face, revealed before its winds arrive. The conclusion for Part 1 is clear. Before a Category 4 or 5 hurricane makes landfall, the atmosphere does not stay silent. It distorts our radios, disrupts our GPS, and fills the air with static. To those who know how to listen, these anomalies are early warnings, as real as a darkening sky. The storm does not hide its coming, it announces it in every frequency, every wave, every distortion. The question is whether we choose to pay attention. Imagine being a radio operator in the Caribbean, listening late at night to distant AM broadcasts, something you have done for decades. But as a storm brews hundreds of kilometers offshore, your radio begins to behave differently. Signals that once carried clearly from Miami or San Juan are now warped, fading in and out unpredictably. The static grows louder, drowning voices with bursts of noise. At first you think the equipment is failing, but then you remember the old sailors saying, "When the radios die, the hurricane is alive." For decades, these observations were anecdotal. Fishermen, ham radio operators, and pilots all reported strange disruptions before storms, but there was little scientific explanation. Today, however, research by NASA's Geospace division and the Jet Propulsion Laboratory, JPL, confirms what tradition long suspected. Tropical cyclones disrupt the electromagnetic environment well before they strike. By disturbing the ionosphere, generating gravity waves, and releasing vast electrical energy, hurricanes leave fingerprints in radio, GPS, and magnetic data that are as consistent as any cloud or tide. One of the clearest findings from NASA's studies is that the ionosphere, the charged layer of the upper atmosphere, shows measurable anomalies during cyclonic formation and intensification. Instruments detect variations in total electron content, TEC, a measure of how many charged particles are present along a satellite-to-ground signal path. Before Category 4 and 5 hurricanes, TEC often fluctuates dramatically, creating conditions that distort or scatter radio waves. This explains why GPS receivers on the ground lose accuracy. Scintillations, small-scale irregularities cause signals to flicker or fade. NASA EOS profiles show humidity and heat rising into the upper atmosphere, but equally important are the electromagnetic ripples those motions generate. The hurricane is not just a weather system, it is a geospace event. Case studies highlight this vividly. Before Hurricane Katrina in 2005, GPS monitoring stations across the Gulf Coast recorded unusual signal fluctuations days before landfall. Engineers initially thought the anomalies were linked to solar activity, but cross-checks with space weather data showed no geomagnetic storms at the time. Instead, the disturbances correlated directly with Katrina's intensification. The storm's massive convection had launched gravity waves upward, disturbing the ionosphere. Pilots approaching Louisiana reported GPS errors that forced reliance on backup navigation, a rare occurrence in modern aviation. To them, the storm's electromagnetic presence was as real as its winds. In 2013, Typhoon Haiyan provided another stark example. In the Philippines, long before Haiyan's eye came ashore, fishermen noticed their radios losing clarity. Some reported total silence across frequencies that normally carried distant stations. Amateur radio operators confirmed that high-frequency propagation had collapsed, unusual for that season. At the same time, GPS receivers in Tacloban logged signal interruptions. Later analysis by JPL showed that Haiyan had triggered ionospheric disturbances visible from satellites, forming wave-like patterns spreading hundreds of kilometers outward. The storm's electromagnetic footprint had arrived long before its storm surge. For villagers, the silence on the airwaves was eerie. For scientists, it was measurable evidence of nature's hidden connections. Hurricane Irma in 2017 repeated the pattern. Coastal Florida residents using personal weather stations with GPS-based timing functions noticed anomalies as Irma approached. Clocks desynchronized, data feeds glitched, and positional accuracy fell off. Local ham radio operators documented intense static bursts that coincided with lightning clusters, forming concentric rings around Irma's core. JPL researchers later confirmed these rings were not folklore, but real electrical structures produced by organized convection. Each ring marked a surge in the storm's energy, reflected in both lightning density and electromagnetic noise. What radio enthusiasts experienced as maddening interference was, in reality, the storm shouting across the spectrum. The science behind these lightning anomalies is fascinating. Hurricanes generate less lightning in their eyes than ordinary thunderstorms, but when rapid intensification occurs, lightning frequency spikes, especially in outer bands. Organized convection separates charges across vast cloud systems, producing discharges that ripple outward across frequencies. Sensitive instruments record these as spherics, radio pulses traveling through the atmosphere. Mariners a century ago noticed their radios filling with crackles before storms, a phenomenon now understood as electromagnetic fallout from cyclonic lightning. JPL's discovery of concentric lightning rings added a new dimension. These patterns can serve as real-time indicators of intensification, perhaps even earlier than wind data alone. Magnetic anomalies also appear in the data. As cyclones churn, their massive electrical activity induces currents in the ionosphere, detectable by ground-based magnetometers. In some cases, slight deviations in Earth's magnetic field occur hours before peak intensification. While imperceptible to most people, some communities historically reported compasses behaving strangely before storms. In the Bahamas, sailors once said their compasses twitched when hurricanes approached. Modern science supports their observation. Electromagnetic induction from storm-related lightning and currents can indeed disturb magnetic readings. These anomalies matter because they expand the toolkit of storm forecasting. Traditional meteorology relies on visible and infrared satellite imagery, dropsondes, and sea surface temperature data. But electromagnetic monitoring adds a new dimension: the storm's invisible impact on radio waves and magnetic fields. NASA and JPL researchers now propose incorporating ionospheric data into forecasting models. If a developing cyclone consistently produces tech fluctuations or lightning rings, it may be on the path toward rapid intensification. For coastal populations, such early warnings could mean more time to evacuate. But beyond science, there is the human experience. Survivors consistently describe the unease of losing communication before storms. In New Orleans before Katrina, residents tuning radios for updates heard only static, compounding their fear. In Tacloban before Haiyan, fishermen abandoned trips because their radios went silent. In Florida before Irma, ham radio operators sent urgent bulletins warning that propagation was collapsing. These lived experiences align with the data. The storm breaks communication before it breaks cities. The psychological impact of these anomalies is profound. In disasters, communication equals security. When radios go silent and GPS falters, people feel isolated, vulnerable and exposed, even before winds arrive. This compounds stress and can lead to panic. Yet reframed, these anomalies can serve as useful signals. Instead of interpreting silence as failure, communities can be taught to see it as a warning. The storm's electromagnetic footprint is already here. Education is the bridge. Just as coastal villagers are taught to recognize receding seas as signs of surge, so too can communities learn that unusual static, GPS errors, or radio silence may be tied to storms. Fishermen who once distrusted silent radios now have the science to understand why. Pilots who encounter GPS anomalies can recognize them as part of the storm environment rather than unexplained failures. Ham radio operators can log and report interference as real-time evidence of intensification. By blending science with lived experience, the gap closes. Of course, skeptics argue that electromagnetic anomalies are hard to separate from space weather effects. Solar flares, geomagnetic storms, and cosmic influences all disrupt radio and GPS, but comparative research shows the differences. Solar events produce global disruptions, while hurricane anomalies are regional, centered near storm systems. By cross-checking with space weather data, scientists isolate storm-driven effects. In fact, the localized nature of hurricane-induced anomalies makes them especially valuable for monitoring specific threats. Case after case proves the consistency. Before Hurricane Sandy in 2012, researchers detected ionospheric disturbances spreading outward from the storm's center. Before Cyclone Fani in 2019, GPS receivers across India logged scintillation patterns directly correlated with storm intensity. Each time, the anomalies mirrored the storm's growth. The electromagnetic signals are not random. They are storm signatures written across the upper atmosphere. Ultimately, these findings remind us that hurricanes are not only local weather events, but planetary phenomena. Their influence extends from ocean waves to magnetic fields, from storm surges to radio signals. They shake not only the ground beneath us, but also the invisible networks that connect our world. The loss of radio clarity, the failure of GPS, and the flicker of lightning across the spectrum are not side effects. They are integral parts of the storm itself. The lesson for awareness is simple. When radios grow silent, when GPS falters, when interference fills the air, the storm is already close. These are not inconveniences to ignore, but warnings to respect. Like the silence of the eye or the retreat of the tide, electromagnetic anomalies are nature's way of telling us to prepare. Because the truth is clear, storms announce themselves on every frequency. Clouds speak in shapes, seas in tides, air in humidity, and the ionosphere in static and silence. To listen across all these signals is to survive. To ignore them is to risk being caught unprepared. Storms are not only visible, they are electrical. Long before the first winds bend palm trees or the first surge drowns the coast, the invisible spectrum of our planet begins to tremble. The ionosphere flickers, radios lose their voices, GPS falters, and magnetic fields shift. For those who know how to listen, the hurricane has already spoken. From Florida to the Philippines, from the Caribbean to Japan, the testimonies are uncannily similar. Fishermen off Puerto Rico describe how their radios go silent hours before hurricanes strike, leaving them isolated on waters that seem calm, but are anything but safe. Villagers in Tacloban recall that before Typhoon Haiyan made landfall, communication with relatives inland had already broken down. Not because of destroyed towers, but because static consumed every frequency. Ham radio operators in Florida before Hurricane Irma reported entire bands collapsing, propagation so poor that even powerful transmitters could barely cross state lines. Pilots in Japan approaching Typhoon Vera in 1959 described unreliable compasses and strange static disrupting communications. These stories span continents and decades, yet they describe the same unseen storm, electromagnetic anomalies marking the arrival of catastrophic cyclones. Science has caught up with what people long noticed. NASA's Geospace Research Division has shown that tropical cyclones disturb the ionosphere by launching gravity waves upward. These oscillations ripple through charged particle layers, altering the total electron content that satellites depend upon. GPS scintillation, rapid fluctuations in signal, is one direct result, making navigation unreliable. JPL studies add to the picture, documenting how organized convection within storms produces lightning rings, concentric bursts of discharges that radiate noise across the spectrum. Each ring corresponds to a cycle of intensification. What radio operators hear as crackling static, researchers now measure as a diagnostic tool. The implications for forecasting are profound. Traditional models rely on sea surface temperature, wind shear, and pressure data. But electromagnetic monitoring adds a new dimension: early detection of intensification. If ionospheric disturbances spike and lightning rings emerge, meteorologists may be able to predict that a storm is about to leap from Category 2 to Category 4. In an age when rapid intensification poses some of the greatest threats, these signals could buy precious hours for evacuation. NASA and JPL continue to explore how space-based instruments can detect storm-driven disturbances in near real time, turning anomalies once seen as nuisances into life-saving data streams. Global comparisons reinforce the universality of these signs. In the Caribbean, sailors learned generations ago to distrust radios when storms approached. In Bangladesh, villagers reported strange silences on shortwave radios before cyclones claimed thousands of lives. In India, during Cyclone Fani in 2019, GPS monitoring stations recorded widespread scintillations as the storm intensified offshore. In the United States, Hurricane Sandy in 2012 showed the same patterns. Ionospheric disruptions rippling outward from the storm, affecting communications far beyond the visible footprint. Each region has its own cultural vocabulary, but the experiences align perfectly with geophysical data. The storm announces itself on every continent, in every frequency. Yet despite this consistency, awareness remains limited. Most disaster education campaigns emphasize visible clues, clouds, tides, winds, while electromagnetic signs are rarely taught. This gap leaves many people unprepared to interpret anomalies as warnings. A fisherman who loses radio contact may curse the equipment rather than flee the waters. A family whose GPS fails may think only of technology glitches rather than atmospheric upheaval. Bridging this gap requires education, teaching that static, silence, and signal loss are not coincidences but storm signatures. The psychology of these anomalies deepens their impact. Survivors often describe the silence on radios as eerier than the winds themselves. Communication is lifeline. When it collapses, fear magnifies. But reframing fear as information transforms dread into awareness. If communities are taught that electromagnetic anomalies are precursors, the loss of radio or GPS can become a signal to act rather than a cause to panic. It is the same principle as recognizing receding seas as tsunami warnings. Knowledge turns danger into survival. NASA and JPL research is moving in this direction. By integrating geospace data into hurricane forecasting, scientists hope to build models that treat electromagnetic anomalies as early indicators. Already, satellites track lightning density, and ionospheric sensors detect TX fluctuations. The challenge is turning raw data into practical warnings, but progress is steady, and each case study adds to the evidence. The long-term goal is clear: to expand forecasting beyond the visible into the electrical and magnetic realms where storms first reveal themselves. History urges us to take this seriously. Katrina, Haiyan, Irma, Sandy, each of these megastorms showed pre-landfall electromagnetic disruptions. Each left behind survivors who remembered the eerie failures of communication. Each was later analyzed in scientific papers confirming ionospheric and magnetic anomalies. The convergence of anecdote and analysis leaves little doubt. These signals are real, measurable, and critical. The question is whether we use them. Because the truth is this: hurricanes are not silent before landfall. They shout in frequencies our technology depends on. They bend the ionosphere, crackle through radios, and scramble navigation satellites. They leave electromagnetic fingerprints as clear as any spiral cloud, and to ignore those fingerprints is to discard one of the few early warnings we possess. For coastal communities, the lesson is urgent. When radios fall silent, when GPS falters, when static fills the air, remember, the storm is already here. Do not wait for the sky to darken or the winds to rise. Those invisible signals are as real as the waves on the shore. Prepare, act, and survive. At Crisis Lens, we believe that awareness is survival. The clues of disaster are not limited to what we see. They are also in what we hear, what we lose, and what our instruments reveal. By learning to read electromagnetic anomalies, we expand our ability to prepare for the storms of tomorrow. Subscribe to Crisis Lens for deep explorations of disaster science, from the tides that vanish to the skies that bruise, from the humidity that suffocates to the static that warns. Share this video with those who depend on communication in storm-prone regions. And remember, the next time your radio goes silent or your GPS flickers, do not dismiss it as chance. That silence may be the storm itself, speaking in the language of electricity.